Yeah, I'm really happy to have this great opportunity to share my research with you all today. My talk today will be about securing cyber-physical systems against the novel physical layer attacks. Oh. So first, just a brief words about my research lab at MSU. I'm leading this Secure and Intelligent Things Lab, SATE lab. And in our lab, we work on three main research areas, IoT and CPS security, AI for security, and blockchain security. So there are some subtopics that we are really interested in, such as 5G security and malware detection, adversarial machine learning, cyber threat intelligence, smart contract security, and so on. So today I'll be focused on our research in this IoT and CPS security field. And just a little information that on our website, as a part of the cyber threat intelligence project, we have developed security posts on the main page of our lab website. This basically posts the latest cybersecurity news. If you are interested, you can take a look at our website and get those information. So I want to start our talk by going through a brief introduction of IoT security. So we all know that the smart IoT devices and systems has gone a long way. From 1994, we have the IBM Simon. That's the first smartphone. Right? At that time, it can only send emails and set calendars. And then almost 15 years ago, we have the iPhone that have revolutionizing the smart devices. And nowadays, we are seeing a more diverse set of smart devices with growing complexity. So we have more and more devices and more complicated devices. And they work on different platforms, hardware and vendors. Unfortunately, those trends has also brought up new vulnerabilities and more vulnerabilities that are more serious. And based on our market research, we know that this year we will have around 50 billion IoT devices. That means that everybody will have 5 to 6 IoT devices with you. And most of these devices have like a small posture, but they are all wirelessly connected. And obviously, IoT has been transforming multiple aspects of industry. And one successful scenario we have witnessed so far is a smart home. Just take this as an example. A smart home is a very personal and sensitive environment. So you all know that those devices like light control, motion sensor, voice assistance, window control, door control, those are all being commercialized, right? So we have IoT products on these different functionalities. I assume that many of you have these devices at your home. And I'm pretty worried about the security of those devices. How do we know that those devices are secure and are not being compromised? And this IoT environment, frankly, they face a lot of challenges, a lot of threats from malicious apps, from malicious sensors, compromised systems, compromised edge networks, and even the wireless interface can be compromised. And adversaries can be inside the home, and they can even be remotely launching the attack to compromise your devices because of the interconnectivity nature of those devices. And obviously, we have seen a tremendous societal impact of IoT security incidents. Like we have seen those denial of service attack launched by those compromised cameras, compromised video streamers. So this has been a big trouble to our internet infrastructure. And smart cars has also been compromised. Even especially disconcerting is these medical devices, such as pacemakers, also have security holes. To really understand the IoT and the cyber physical security threats, we need to look at the history of IoT security vulnerabilities. And we can see that nowadays they are becoming more technically sophisticated and better organized, and they are really harder to detect. And IoT systems can have vulnerabilities. Oftentimes, those systems have components from different vendors, and they are developed by different companies, and they are maintained by different developers. So this kind of diversity gives out a lot of vulnerabilities. And malicious code and botnets has been compromised a lot of devices, IoT devices. Because of the limited resources of IoT devices, you don't have sufficient defense mechanisms implemented in them. And we have seen a growing incidence of DDoS attacks towards website and cloud infrastructure. And adversaries are becoming more capable, and they are defense aware. So they know what kind of defense you have, and they are aiming to bypass your defense. So as a defender, we really want to ensure that our system is secure, private, reliable, and robust against those adversarial attacks. And in this talk, I'm going to talk about a new physical layer attacks towards voice assistance and new physical attacks towards camera of autonomous systems. And then I will describe some of our other research problems. If you have any questions in the middle of my talk, you feel free to interrupt me, and we can address them. So the first thing that I will talk about is voice assistant security. You know that the voice assistants are very popular, and some of the most popular voice commands include those like read my message, calling someone, send a text message, and even some smart home device control, like open my garage door. And a lot of questions such as what's my schedule and what's the weather today. So we have seen that these voice assistants are really want to bring up a pervasive future using voice control. And these big companies like Google and Apple, they are imagining giving more power to the voice assistants. However, like those voice assistants are not robust to a lot of attacks. And there are so many attacks that have been proposed, like the over-the-air inaudible attacks. We have seen several inaudible attacks. The attacks can control your device without any audible voice. In this case, when the attack happened, the victim basically cannot notice anything. So the insight is that we can send some human inaudible commands using ultrasound. Ultrasound is at a higher frequency that human cannot hear, but the machine can take it as a commands to interpret it and then control the voice assistance. And here we have basic elements included in this microphone. However, due to the non-linearity of the diaphragm and amplifier, we know that the output signal will contain some higher order components. Right? In the ideal case, you will just have an amplified input signal, but actually it will contain some higher order components. So if we send two different waves using ultrasound frequency, the output of amplifier will include some low frequency components like F1 minus F2. So this component will be falling into the range of the audible range, and that can be interpreted by the microphone as a valid command. So with such over-the-air attack possible, we are thinking about whether we can deliver the attack signal, that means the ultrasound attack signal through other medium. So naturally, you would think about a scenario when people in a typical office, coffee shop or in an airport, people put down their phones at their side and type on their computers or read books. So usually they pay less attention to their phones. So it gives us an opportunity that we can propagate the attack signals through the solid medium such as a table to reach the mobile device to attack it. So here we have a typical attack setup when we place a piezoelectric transducer. This is a transducer that can transmit ultrasound waves. We place it underneath the table to generate ultrasound guided waves. And then the guided waves will propagate through the table to reach the device on the top of the table to attack it. And this transmission media can be different types of tables. So the basic idea is just to use a solid media as a transmission media to launch such inaudible audio attacks. So here comes our attack. We call it surfing attack. Basically, it's like a surfing waves in the materials to attack device on top of the material. So on the left-hand side, we have seen this mobile device was activated by a transducer placed underneath the table. And the good feature about this attack is that it's non-line of sight, right? It's omnidirectional. So anything placed on top of any device placed on any area of the table can be attacked. And we also demonstrate such long-range attack, like using a long aluminum metal material. So this is a 30 feet long aluminum metal material, and we transmit the signal that can reach the device to activate the voice assistance, and can also attack multiple devices simultaneously. So as a realistic attack scenario, we put like a table clothes on top of the table, and then put a transducer, for example, on the side of the table underneath the table clothes. And then when the attacker launches the attack, the device will be activated, and then starts sending some commands. So you can see that beside this phone, there's a water. There's no vibration that can be sensed. So this phone now is calling someone that the owner of the phone has no awareness of that. Basically, what I want to show is that victim basically cannot feel any vibration or any unnoticeable sound from such attacks. But if the signal can be delivered successfully to the phone, it can really cause a lot of damage. So you may wonder how it works. And the basic idea is I already described that we want to use this ultrasound guided wave, or called so-called LAM waves. You may have learned about LAM wave in your high school physics. And this LAM wave or ultrasonic guided wave is very popular or very widely used in the civil engineer, used to inspect and screening many engineering structures, particularly for inspecting those metallic pipelines around the world to discover some structural damages. And this guided wave have 3 unique properties. Unlike the over-the-air audio acoustic waves, the guided waves have wave dispersion, and they have multiple wave modes. And the acoustic waves, they enter the solid medium, they can disperse into different wave modes and at different frequency and at different propagation speed. Right. So if you transmit over the air, you only have one frequency signal, and you only have one propagating speed. That's the the speed of light. But in the materials, the ultrasonic waves, they will be dispersed into different wave modes with different frequency and different propagation speed. And this propagation not only depending on the frequency, but also on the material and the geometry of the structure. So here you can see that the wave is dispersed into 2 different types of waves. Like the first wave is much faster, and there's a second wave. I'm not sure you can see the animation, but the second wave is lower speed. And these different modes of wave eventually they will interfere with each other. So any questions? So we are trying to select an attack wave that can carry the audio signal or voice signals to attack the device. In order to select it, we have several requirements. We want the attack wave to have low dispersion. So in order to achieve that, we just design the signal as a narrowband signal. And then we want to have a low attenuation. So this ultrasonic guided wave at a higher frequency, they have a very low attenuation transmitting along the materials. That's why it was used for the hundreds kilometers of metallic pipelines in the first place, because it can propagate very far. And it can be easily excited. We can use the piezoelectric disc. It's very cheap. It's $5 per piece. You can purchase off the market. And the attack can reach the device at a high attack signal strength. So in order to do that, we need to select LAM wave modes. So as I said, we have different modes for this LAM wave. And we select the mode as A0, because A0 mode has this vertical shape of vibration, and this can reach the device at a better signal strength. And after we select the wave mode, we want to generate the attack wave. The basic idea is to preserve the similarity between the recovered voice signal and the original signal. So here's our modulated signal. You see that we have a modulation depth, and this is the baseband signal, the voice signal itself. And then we modulate that onto the central frequency, that is ultrasound frequency, that is very high frequency. And then we apply a turkey window to shape the signals. And then we optimize the central frequency modulation depth and the turkey window by measuring these nonlinear responses. So for each device, for each mobile phone, you have different set of best parameters that you can select to launch such attacks. So here we show an example of turkey window signals. So this is original voice signal, and the bottom two are the signal that is recorded by the voice assistants. We can see without the turkey window, some signals are lost. But when we apply the signal, when we apply the window, the signal are much more powerful, and the shape is much better. So in this case, the microphone can recover the OK Google, this command. And we want to validate whether the ultrasonic guided wave can trigger the non-linearity response from the microphone on the table. So we run experiments, and we send this baseband voice signal from this transducer, and then we record the voice signal from the smartphone on top of the table. We can see that the recorded voice signal includes these two harmonics, and the first harmonic signal is actually the exact same as the original voice signal, although the strength is much lower, but you can still see like the shape is pretty much the same as the original signal. So in this case, the baseband signal is modulated to 25 kilohertz frequency, so human cannot hear it. So this demonstrates that we can really trigger the non-linearity effect from the microphone by sending the signal through the material. Then here comes our system. So first, we want to convert the voice commands into the speech by using a text-to-speech module. This is a off-the-market TTS that you can use. For example, you have Google TTS that is very easy to use. And then we synthesize the victim's voice using some synthesis approach. And after that, we can send the synthesis speech to the signal processor. So this is attack device, and the left-hand side controller can be a remote controller. And at the attack device, so how this is sent, it can be sent through the Wi-Fi or Bluetooth to deliver it to the attack device. And then the attack signal will be used to activate the transducer to inject the voice commands. And the response will be captured by a tapping device, and the response can be sent back to the controller to basically to analyze the response and send a follow-up command. And this interaction loop can continue. So this is our prototype system. We have a waveform generator that is controlled by the laptop to generate the attack wave. And then the attack wave is delivered to the piezoelectric transducer underneath this material, and then attack this smartphone on top of the table. And you can see that this piezoelectric transducer is a very small component. You can hardly notice it. So just to show some attack scenarios, you can use it to steal some SMS passcode. For example, you can first ask the phone to turn down the volume, and then you can read the message. Then the typing device can capture the message and interact with this voice assistant to steal this message, to steal this passcode. And you can even launch a ghost call to call any friends or family members in your phone content, right? And that call will be so the owner cannot hear it, but actually can go through the voice assistance to call your friends, right? So this call can be made using synthesized voice from the owner of the device. And as I said, this multi-round conversation has a real security impact. It can be used to steal financial and trade secrets, right? So it's it has really a large impact. So now I want to think about like when we have this inaudible attack that can really reach the device, and then what's next? So what kind of attack are still possible, right? And we have seen this long list of attack signal modalities, like EMI signals, like hidden voice, like ultrasound signals, like guided waves. That's our own work, and like laser and light. That's from the light command work, right? And surprisingly, this EMI signal injection to inject voice signal, that's actually the earliest work in 2013, using EM waves to generate to inject voice signals. I know Sharon has been working on the EM signals, so this modality is has been worked a lot. And also we want to think about the voice attack mediums. Now we have seen the over-the-air attack. We have seen the solid materials as a medium, and also underwater attack medium. So what's next? So what medium are still out there can be used to launch such voice attacks? So we are continuously we are keeping thinking about this problem of developing a new signal modality and developing new attack mediums. Yeah, again, think about this problem that how about inaudible attack through other media and other signals. Then we come up with the idea that maybe we can transmit the voice signals using the charging cable. So charging cable is driven by electric signals. Electric signals and the voice signals, they are completely different, right? So we are thinking about whether we can inject electric signals to actually trigger the audio, the audios from the microphone. So we have seen that those shared battery pack are quite popular nowadays, like especially in the Asian market, especially in China. There's a lot of charger sharing companies. One is backed by Alibaba called Energy Monster. So they have a lot of shared battery pack that you can borrow and plug into your phone to charge your phone. So no one has really thought about the security impacts or security implication of those shared battery packs. So we think that maybe it's good opportunity that to launch attack through this battery pack. And if we really make it successful, this attack can be interactive. It means that the attack can be used to inject signals. It can also be used to eavesdrop the signals. And it is robust against noise. So whatever noisy environment you are at, it doesn't matter, right? Because you are inject the signals through electric signals, not audio signal. And we can also bypass the voice authentication, right? So usually a lot of voice assistants, they have voice authentication. So only the owner can activate the device. However, using the electric signals, we can bypass this authentication phase. Okay. Any questions?
Qiben, I have several questions here.
Oh, yeah, sure.
The first is, what's the kind of device that you are using for perform the attack?
Perform this attack?
Yeah, what any commercial device that you can use to? I know that now you just generate the signal, but like in the practice, so what kind of device that can be used to perform this attack?
Oh yeah, yeah. So the practical scenario, you only need to generate these signals, right? So signal generator. Right now we are using this powerful waveform generator, but in fact, in reality, you can also use mobile device. So mobile device can also create or generate some attack signals, and this can be used to actually to activate the transducer as well.
Okay.
So you use a mobile device and connect the mobile device to an amplifier to amplify the signal, and then connect to the transducer, and this can be and this can also be used to launch the attack.
Okay. So and also I saw that for the bandwidth, like the central frequency, you need to modulate to the 25 point something kilohertz, right?
Yeah.
But based on my knowledge, I think the most of the smart device they only send out the ultrasonic signal up to 24 kilohertz. Have you ever try to use some smart device to see if they can send the signal at the 25 kilohertz?
Yeah, definitely. So right now the current mobile phone, they cannot send 25 kilohertz, but 25 kilohertz, this is just an example. So it actually can be 24 and 23, 21. It depends on different target device. So
Okay.
if you, so we have a table that lists in our paper, like what's the best frequency that we can use to attack different smartphones. So sometimes it's 21 kilohertz, sometimes it's 22 kilohertz. So that it varies.
So it's not the strict requirements, right?
Yeah, it's not a strict requirement. It's so you have a range. You have a range of available frequency that you can use to launch to launch such attack.
Okay. So one more question. So now I saw that you experiment. So it's using the smartphone. But if the smartphone is locked, so it has a password. So how can you pass this authentication? I know that for the other voice assistant system is possible because they just use the voice to activate this. But if for the smartphone, how can you pass the authentication step?
Yeah, that's a really great question. So so it's not easy. So it's not easy to activate the device without passing the voice assistant, without passing the voice authentication. And in order to do that, one way you can do is to synthesize the owner's voice, right? So you can record some of the owner's speech. For example, you capture you find some YouTube videos from the owner's speech, and then you synthesize the voice, and then use this voice to activate the assistance. But definitely, this is a lot of work. Yeah, we say that. So you need to bypass the authentication. Is actually quite troublesome. Yeah.
Okay, I see. Thank you.
Yeah. So this actually lead to our current work, that this charging cable attack, that we can actually bypass the voice authentication.
Okay.
Because now you are not using the voice signal, you are using electric signals.
Yeah, that sounds great.
Yeah, thank you. Any other questions?
I have a quick question.
Yeah.
So in the GhostTalk attack, do you use inject the baseband signals, or do you modulate the audio signals with with a high frequency or a resonant frequency?
Yeah, it's baseband signal, so it doesn't really.
Okay,
we don't really need to transmit ultrasound. Yeah, I'll talk about that actually in a few slides.
Okay. Thank you.
Thank you. So yeah, so let's move on to the GhostTalk attack. So now this GhostTalk attack basically comes out the idea that we can use a new modality and a new media to transmit the attack signal. So we have seen that the smartphone manufacturers now they have removed the headphone jack, right? So now all the newer smartphones they don't have any headphone jack, and this is a controversial step from the Apple, but actually now all the smartphone companies they follow suit. Now we have these two different very popular standards called the Lightning port and the USB-C port. So both of them support both the power supply and also the audio signal transmission. So when we deassemble this charging cable, we can see that this charging cable contains both audio wire and a charging wire, right? And we are thinking that maybe these two wires, they are interfering with each other. For example, when I inject electric signals into the charging wire, this can introduce some audios in the audio wire. Or if I have some audios in the audio wire, I can actually incite some like frequency vibrations in the charging wire, so I can actually capture the audio signal, right? So this is the idea that we are thinking about. So we want to validate the attack feasibility, and then first we modulate the voltage signal like using an audio signal. So that's a baseband audio signal. So this is the voltage, right? And then we measure the recorded audio, and we can just see that the recorded audio contain the shape of this modulated voltage, right? So it's quite surprising to us, but actually we can use it to inject audio signals. And vice versa, when we are playing the audio on your mobile device, we try to capture the voltage. And actually we can see that the shape of the voltage measurement follows this audio signal, right? So that means it can be used to eavesdrop the audio signals from the electric signals. Basically, the electric signals can become a carrier to inject and eavesdrop the audio signal. So now this has a real implication that when we are, for example, when we borrow a power, a charging pot or a charging battery pack from a company, and then we have a modified cable, right? So this cable is modified by us. And then the attacker can inject signals through this modified cable to attack this device. And it can also eavesdrop the conversations when you are speaking to the mobile device. This conversation can go through the wire to send it to the attacker. So here comes our GhostTalk system design. And on the attacker side, attacker can launch the attack remotely, and it can inject audio in the form of electric signals, and then inject to the microphone. And on the other side, the attacker can also embed a voltage measurement circuit into the charging cable to measure the voltage. And then using the measurement, it can be used to recover the audio. So the nice thing about this attack is that we can actually, using a functionality, a feature from the mobile device. So as you have experienced that when you click some buttons on your earphone, it can actually activate the voice assistance, right? I mean the buttons in your earphone cable. So this button click feature can be utilized by us to activate the voice assistance without using voice authentication. So here we simulate this button press behavior using a MOSFET. So this MOSFET can activate this button to activate this voice assistance. And after the voice activation, then the attacker can inject the audios into the voice assistance to launch some attacks. And then it can also eavesdrop the audios. So in order to improve the injected audio quality, we add some components to smooth out this injected audio, right, to make sure that it can reach the device properly. So here are some GhostTalk attack scenarios. I will quickly go through them. Like the first one is we can try to call someone to steal the password. And then we can try to get some private information from your friends. And we can also use it to hack into the verification code. Right? So the one thing that I want to point out that is this attack requires a modified cable. So what happens if we have no modified cable? So you are using your own cable in the public charging port, right? So you cannot really inject signals. So in this case, we can still recover the audio signal. We can eavesdrop the signal from the electric signals. For example, when you are charging your phone using a public charging port, and the attacker can embed some voltage measurement behind this port, and it can actually capture the audio information from the electric signals propagate through this charging cable. So the question is why the audio signal can be extracted from the power side channel. And one hypothesis is that it may come from the EM coupling. So EM coupling between the audio wire and the charging wire. But we found out that this is not the case. And we do an experiment using a phone with multiple speakers. And we have a bottom speaker and a top speaker. So, oh, sorry, this is a microphone, top microphone and a bottom microphone to capture the signal. So we know that the EM coupling is highly relevant to the location of the receiver, right? So if the receiver at different location, the received signal will be different. But as we can see in this case, the top microphone and the bottom microphone, they can actually receive pretty much the same signal, same audio signal from the electric signal. So that means that the audio signal pattern is not generated by the EM coupling, but it is leaked due to the high power profile of the loudspeaker itself. So the loudspeaker of the mobile phone have a very high power compared with other components. And this power can actually be leaked to impact this audio wire. And then the audio wire will carry this signal over to be converted into an audio signal, right? So this is the theory behind why this eavesdropping attack can really happen. And we designed this cable eavesdropping attack by just a simple voltage measurement circuit. And in order to recognize the words and the digits better, we designed a neural network to classify the digit, right? So this neural network follows traditional CNN architecture, CNN ResNet architecture, to make sure that we can recover the digit of words accurately. So as you can see, this is our attack hardware. It's pretty small. It just includes a small microcontroller and some cables, and it's a portable device, and it's very small. It can be embedded into a power bank. So we launched this attack to 9 different smartphones, and show that the injection can be happening with 100% access rate to attack all types of smartphones voice assistants. And we also did the eavesdropping attack, and we see that the eavesdropping accuracy is pretty high. This is the accuracy of recognizing the digits, like 1, 2, 3, 4, and we want to see how accurate we can recover the audio signal from the electric signal. And this Pogo phone is an exception. It has a low accuracy because we found out that the noise, the background noise in this Pogo phone is too much. And you can see that when you are running a lot of apps, the apps also generate electric signals, right? It's a background noise. It can impact our accuracy. And also we tried the attack with different volumes of the speakers, and when the high volume and the low volume, so they have different captured voice signals. And there's a high correlation between the volume and the classification accuracy, right? So that's pretty obvious. For countermeasure, you can simply disable the voice assistant activation using headphone. And we can also add some headphone notifications. So when you embed when you plug in a headphone, you should have the owner should be notified. And you should stop charging when you are reaching a high battery level. As a summary, that this attack can really happen through the solid medium and charging cables. And we envision that there are other types of physical voice attack that is still possible. Okay. So follow up on this direction, we are thinking about there are two complementary directions. One is audio eavesdropping. So we have seen the audio eavesdropping through hidden microphone, motion sensor, wireless signals, and the LiDAR and the vibrations through the light bulb, and now using the power line. So what's next? So what kind of other signals can still be used to eavesdrop audios? And on another direction, you can think about like power side channel. It has been used to do cryptanalysis, app fingerprinting, screen contact leakage, and the button click leakage. And now it can also be used to eavesdrop audio signals, right? So you can think about what's next, what kind of attacks that can happen with a power side channel. And we are thinking that it might be interesting to connect such physical attacks with a very popular model adversarial attacks, right? So attack this physical can actually be used to attack the models behind the voice assistance. And here are some of our recent work try to launch the audio adversarial attack in a black box manner to attack the voice assistance neural network models. And then we can think about defense to defend against such attack using some better neural network designs. Before I switch topic, are there any questions?
This is Yazo. I'm from Dr. Hayes lab. So yeah. So thanks for the amazing work. I mean, I've been following reading your papers from I guess 2 years ago, and so for the GhostTalk attack, I saw the two microphones, so they are showing different readings in the attack, right?
Right. So
is it possible to detect the attack by utilizing multiple microphones?
Yeah, absolutely. So
okay.
Yeah, using multiple microphones, or even you can use multiple like sensor fusion. I assume that this audio injection or electric signal injection can also impact other sensor readings, and you can read it from other sensors, for example, gyroscope or some other vibration sensors, to see whether you have these injected audios happening there. Right, you said so using multiple microphones to measure the difference. Yeah, so that definitely can be an effective defense.
Okay, thanks for answering my question.
Thank you, Yazo. All right, so let me quickly go over another attack towards the camera of autonomous systems. Yeah, I'm a little bit behind, so I will be pretty quick. So now we know that the cyber-physical systems like autonomous driving, they have a very important task to perceive the environment, right? Do object detection and object tracking. And And in order to do this perception, you require some sensors, right? So those are four very important sensors: LiDAR, camera, radar, and acoustics, that has been used in autonomous vehicles, in drones, to do this perception task. So we are thinking that how secure it is for the depth estimation with a stereo camera. Stereo camera is a 3D camera that can be used to get the depth information from a 3D environment. And in the autonomous vehicles, usually you use LiDAR to get the depth information. But in the drone or in those robot cars, small vehicles, you will not use LiDAR because it's too expensive. So what you're going to use is those stereo cameras. Stereo cameras can be used to get the depth information just like LiDAR. And in this attack, we are attacking this camera or stereo camera to inject some signals into the camera to inject some fake depths. And you can see that the impact is obvious, right? So if you are driving a car, if a fake obstacle appears ahead of your car, then it might cause some damage, right? And if you are a drone operator, if drone see a fake obstacle, then it may be changing the routes. So there are some existing works like using laser to attack the camera, right? But the work has shown that it actually can damage the camera. And we have seen that projection attack by projecting light into the normal camera to project those stop signs. And we can also see this projection attack to project images on the road, right? So let the autonomous vehicle see this projected image as a real human or a fake obstacle. So in this case, we are attack this stereo camera. And the uniqueness of stereo camera is it's actually perceives the environment using a triangulation, using two cameras to perceive the environment to get the depth information, just like our human eyes. And the vulnerability that we discover is that the camera system, they have a problem of identifying the objects. So they want to match the objects when they are similar in shape and they are similar in color. For example, I can just add an image patch on two different places, on the left image and on the right image. And then these two images will get into the perception algorithm of the camera system, and it will create a fake depth, right? So the idea is pretty simple. And this fake depth can be generated by adding this two patch. And to do this two patch, to add this two patch, we can basically use a flashlight. So here's an example that use a flashlight of the camera of a smartphone to inject the lights into the camera, right? So in the camera, you can see these glares and orbs, and these are the objects, or so-called patch, that apply to the camera image that can generate fake depths or fake obstacles. So this is a really good opportunity to inject this fake depth information. So in this attack, we just use two flashlights or two projectors to inject signals to the drones, to the cameras to launch attack. Right. And the attack is also very simple. So we just use two light sources and just to change their location and direction, projection to directions to create those orbs and glares so that the signal will be mapped differently. So you can see there's a fake depth and fake obstacles being generated. And by changing the location and the direction of these two light beams, you can actually create different fake depths. Right? In this case, in this trapezoid shape attack, we can create a far distance object. Right? And this is another type of attack that we can, the human operator can just control two light sources and adjust the direction to launch such attack. And we did a simulation on autopilot and AirSim to manipulate the depth information. And you can see that this drone's direction, this Jones routes can be manipulated by injecting this fake obstacle into the scene. And using this real experiment, we're using 2 projectors, or it can also be 2 flashlights. Then inject the light into the DJI drone, and then the drone will react differently. So in this attack, we see that when we project light at night and at daytime, it will be very different. So this is a fake depth range at night and a fake depth range at daytime. We see that at night, we can launch this triangle attack at maximal 15 meters range away. And at daytime, we can launch attack at 8 meters away. So this can make the real-time drone control be really possible, right? As demonstrated in our simulation. So for example, in this attack, in this daytime attack, you can see
Takeoff.
these 2 light projectors
Please check it on the map.
are projected to this drone, and this drone will perceive a fake depth information on the screen. And then when the pilots try to push the drone forward, it cannot, because there's a fake obstacle ahead of it. And this can cause some sudden brake and can drift away the drones and can also shake the drones. And similarly, we can launch the attack at night. So for defense, we can basically enhance the hardware of the camera by applying some algorithms to detect the oversaturated pixels. And we can also apply some new hardware like a camera lens hood or film polarizers. And as I mentioned, we can also do sensor fusion, right? And design robust neural network models to detect this light injection attacks. So in a summary, this DoubleStar is a long-range attack to depth estimation algorithms in the autonomous systems like drones. It can achieve 50 meters attack, 50 meters range attack distance. So we are thinking about what's next, right? So whether we can launch in the same type of projection attack towards LiDAR, camera, and normal camera, and radar, and even like 3D or 4D image radar, and also try to compromise the fusion models that are used to fuse the data from those different sensors. Right, so that's all possible research directions. Yeah, just briefly about my other research problems. I'm also pretty interested in working on this wireless security, like launching jamming attacks and false data injection to the Wi-Fi, to the public Wi-Fi systems. And we are also seeing this speaker verification. So current speaker verification requires a huge amount of data, right? So it requires 3 million data in the Google speech recognition system, but we are trying to improve it or reduce the number of data that we need by using the high frequency signals in the human voice to basically make the voice verification more efficient. And we are also doing attack towards the smart contract systems in the blockchains, and discover some social engineering attacks, and try to steal money from the hardware wallet by attack the clipboard systems on your computer. And also design the efficient systems to improve the blockchain efficiency. Like we develop self-service system using blockchain for vending machines. And we can also improve the scalability of the smart contract execution using cloud systems. Finally, so this is a multi-layer view that I want to really put forward here. So we want to know that there are 3 different levels that are really interested to our security researchers. So the first one is the things layer, those devices, sensors, and the connectivity layer. Those are the communications networks, and the application layer. Those are the applications and the neural network models and human-computer interactions. And as part of my research, I want to explore those things layer by discovering the vulnerabilities and securing the wireless communications, and also securing the building systems to secure the cyber-physical applications and blockchain applications. I'd really like to thank my students. These studies will not be possible without their hard work.